Very good. So let's start with the next lecture that is on linear programming. So linear programming is, well, this is the layout of the lecture. So linear programming is a set of problems in which we have linear constraints and linear goal function. So we have, for instance, let's say that a farmer owns 100 hectares of land to allocate between wheat and corn. So there are two variables that we want to, what is the surface of wheat, what is the surface of corn that we want to culture. And then the aim is to maximize the profit considering the budget and labor constraints. There are some parameters here. So the profit by hectare of wheat is 300, by corn is 400. So as we want to maximize the profit, so should be 300 times the hectare that we, the surface that we dedicate to wheat, plus 400 the surface of corn should be maximum. But there are some constraints. So each one of these surface units, they cost 120 euros, corn 200, and then these ones require 10 hours of labor. These ones require 20 hours of labor. And we have a total amount of land, budget, and labor amount. So the total surface has to be smaller than 100. That is the maximum we have. Then the budget that we have for these activity is 20,000 euros. And because the cost per surface unit of wheat is 120, so it will be the cost of the surface associated to wheat will be 120 times x1, and then plus 200 the surface, the cost associated to corn, and this has to be smaller than the total budget. And the same for labor. So we have in total available 1,200 labor hours, and then each one of these surface units, they take 10, each one of these take 20. And we want to maximize this profit, but subject to these three constraints and the non-negativity constraints, because both surfaces have to be larger than zero, or larger or equal to zero. Okay, so we can try to plot all these constraints and all the, to see how they look like. So let's start with the land. So this is the surface of wheat. This is the surface of corn. Maximum, but they have to be smaller than 100 because you don't have more than 100 hectares. And then the land has to be x1 plus x2 equal 100. Has to be a smaller or equal, but let's draw the equal one. Okay, so this is this one here. So it's this line, and then smaller or equal is this all this area. Okay, very good. So then the budget is 120 x1 plus 200 x2 has to be smaller or equal to 20,000. So this is this one. And then the same for the labor. And then we can draw some lines. So what are possible profits? So let's say that we have, let's say that we say this profit, this is the profit, and we want to maximize the profit. But let's say this profit is equal to some number, and we try several numbers. Okay, so what are the properties of this problem? So first we have inequality constraints. So inequality constraints mean the solution has to be on this line to the lower part, from this line to the lower part, and from this line, the green line, to the lower part. So if you compute the intersection of those three areas, and they have to be larger or equal zero. So they have to be in this axis upwards. Okay, so if you compute the intersection of all those areas, the intersection area is this blue region. And this blue region is limited by the constraints. By here it is two of the constraints, but it could be by any number of constraints. But in general, this will be a kind of polygon. Okay, then what about the profit? So the profit, we have drawn here different lines. And what we see is that as you go in this direction, the profit is increasing. So we could have drawn some more lines. Actually, we would see, and all these lines are parallel to each other. So probably the maximum value is here. It is in this corner. So it is, you push the profit forward until you reach the last point of the feasible region. On this area, it's the feasible region. So you push the profit until the last point that is still feasible. It would be this column. So in general, we will see that later in more detail, but the solutions of these linear programming problems, they all have the same characteristic. So the profit, the goal function is a line, not a line, it is an hyperplane. You remember that these kind of equations here, they were hyperplanes in the two-dimensional space in this case, and hyperplanes in 2 dimensions, they are lines. So that is why we have these lines. But in general, they are hyperplanes. The feasible region is always a kind of polygon. Polygon in 2 dimensions, in n dimensions, it is called polytope. And then the maximum value will be in one of the vertices of those polytopes. Okay, so we have this kind of structure. Okay, more problems, so more problems that are similar to this one. So let's say that a company must ship products from 2 warehouses to 3 retail stores. And the goal is to minimize the transportation cost while fulfilling the store demand and not exceeding the warehouse supply. Okay, so we have 2 stores, we have, 2 warehouses, 3 stores. Warehouse 1 can supply 100 units, warehouse 2 can supply 120 units, and the demand of store 1 is 80, the demand of store 2 is 70, and the demand of store 3 is 50. And the cost for selling from warehouse 1 to store 1 is 4 euros, warehouse 1 to store 2 per unit, it is 6 euros actually. And then we want to minimize the total shipping cost. Okay, so here the variables that we can touch are the x11, x12, x13, and x21, x22, x23. That is how many units you are sending from a given warehouse to a given store. So x13 is how many you are sending from warehouse 1 to store 3. And if you write that, it is this thing. So it is what is the cost from sending from warehouse 1 to store 1 times the unit cost, and from 1 to 2 unit cost, or that's 1 to 3 unit cost, and so on. So you want to minimize this, but there are some constraints. So the constraint is the capacity of warehouse 1 is 100. So whatever you send from warehouse 1 has to be smaller than 100, and the capacity of warehouse 2 is 100. So whatever you send from warehouse 2 has to be smaller than 150. And the same for the demands. So the demands have to fulfill the demand of each one of the stores. So whatever you send to store 1 has to be 80, because the demand of store 1 was 80. And this has to be 20, 70, 50, and then whatever you send has to be larger or equal to doesn't emit these negative portions. Okay, so again, we have the same structure. So we have a linear function to maximize or to minimize. Then we have non-negativity constraints. We have some equality constraints and some inequality constraints. Let's look at a different problem, but the structure will be the same. So let's say that you have $100,000 that you want to allocate between three assets. You have stocks, bonds, and savings account. The goal is to maximize the expected return, and then you have what is the expected return in each one of the assets. And there are some constraints that we will see later. Whatever you decide is how much to put into each one of the assets. So X1 is the amount invested in stocks, X2 in bonds, and X3 in savings. So how much we have in cash. And then the constraints. So the constraints in total, we have 100,000. So the sum of the three has to be smaller than 100,000. Then there is another constraint. That is that you don't want to put more than 50% of the total investment in stocks, so just to limit your risk. So this is the total investment, and then X1 has to be smaller than 50% the total investment. And then at least 20% has to be kept in savings or liquidity. So if you need to do some urgent payment or whatever. So 20% of the total investment, X3 has to be larger than that. And all of them has to be non-negative. And then again, we have the same structure. So the structure is a goal function, but it's a linear combination of some variables, and then inequality constraints. All of them are inequality constraints, and we don't have in this case equality constraints. So in general, the problem structure will be this one. So you have some linear function to maximize or to minimize. Here we have put it as always as a maximization problem, but you can convert the minimization problem into a maximization problem simply by multiplying by -1. So there is no problem with that. Then some constraints, and the constraints are always non-negativity for these variables, and then equality constraints and inequality constraints. And this is the general problem. And we already learned last week to add slack variables so that we can convert all the inequality constraints into equality ones. So simply by adding some slack variables that account for the difference. So at the end, you can put everything into equality constraints. And then there is a matrix form of that. So the matrix form, you see now our unknowns are X and S, but the goal function is only using X. So the coefficient multiplying S has to be 0. And then what about the equality constraints? So the equality constraints has to be AX plus S equal B. So AX plus S equal B. And then X and S have to be both larger than 0. So you can put this problem as a matrix problem. So it is simply a matter of writing how you write them. Any question? Okay, so now let's solve it. So the solution of that, what we will do is, so we have a polytope, this n-dimensional generalization of the polygons. And then what we will, actually, this polytope, the sides of the polytope, they're also defined by hyperplanes. Again, this problem was two-dimensional, but an hyperplane in 2 dimensions is a line, but the polygon had some lines defining the sides of the polygon. So in n dimensions, it is the same. You have hyperplanes that are defining the sides of the polygon. And then these hyperplanes intersect into lines, and if you have 3 or 4 or whatever, they intersect into points. So those vertices, so we will navigate the vertices and evaluate what is the goal function in each one of the vertices. And we have to start from some feasible solution. So you start with something that is feasible, and then, so in one of the corners, and then you start moving. And yeah, so all this we will see across the along the example. Okay, so this one of the methods to solve this linear problems is this simplex method. This is the one we are explaining now, so the one that goes through the corners. So the first step is to convert the linear problem into a slack form. So you convert all inequalities into equalities. Then you initialize with a feasible solution. You identify one entering variable, and you have to determine one leaving variable. We will see that in the example. And then there will be a table. This table, you will pivot over some element. And this pivoting is the same as when you were solving linear equation systems with matrices. We will see it, right? And then you iterate until you finish. And the ending condition is that you cannot get in any other variable into the solution, to the basic solution. And then the geometric interpretation of this process is that you are going from one corner to the other corners. Actually, this makes a lot of sense because you can, all this, if I want to determine this corner, I have to compute the intersection between this hyperplane and this hyperplane. So the solution of this is this corner, and the solution of this is the solution between an equation system in which we have this hyperplane and this hyperplane and so on. So solving linear equation systems, it is actually what we are doing with the pivoting and that. So what we are doing is solving an equation system. Okay, so I suggested you to watch this video before. Actually, we will see it together. There's no sound, I think. Probably, even it is better if there is no sound. Let's have. And must be, yeah, this one. So he's explaining it. It's very, very well. So I will follow the same path, reasoning path. So let's say that you want to maximize this function subject to these constraints. Okay, then first thing is to convert it to the slack form. So the slack form is adding two slack variables so that we convert these inequalities into equalities. And the rationale behind this is that, okay, this will be smaller or equal 16. So let's say it is this thing, let's say it is 13. So if it is 13, we need to add 3 to reach 16. So this is the meaning of this slack variable. Let's say that this is already 12, and then we don't have to add anything, and then S2 will take value 0. So first we convert from inequalities to equalities, and we have this constraint that all the variables here have to be 0. And yeah, the slack variables do not take part of the goal function. So the coefficients here are 0. Very good. Then, yeah, this is our problem we have to solve. And we need to start with some feasible solution. Okay, so let's see if we can find a feasible solution. So let's say, okay, I have 4 variables. I have to find some combination of four values such that we fulfill the constraints. So you don't know where to start looking. So you start saying, okay, let's say that x2 and s1 both are 0. If x2 and s1 are 0, then this term disappears and x1 takes value 8. Okay, so x1 takes value 8, and now x1, that is 8, you substitute here, x2 is 0 by assumption, s2, so it has to be that s2 is minus 12. So, but s2 minus 12, so you have found this solution starting with 0, 0, so x2 equals 0, s1 equals 0, you have found 8, 0, 0, and minus 12. But this is not feasible because S2 is negative, and one of your conditions was that all the variables had to take positive values, non-negative values. Okay, so yeah, this is infeasible, and so let's try to look for something else. And something easy is x1, x2 equals 0. So x1, x2 equals 0, you are already satisfying this part. And okay, so both are 0. So if both are 0, then all these parts disappear, and S1 takes value 16, S2 takes value 12. And this is a feasible solution. So always in this kind of problems, setting the original variables to 0, not the slack variable, but the original variable to 0, will always give you a feasible solution. Always. Okay, so now we have feasible solution. Now what we will do is to write, we will write the, what is called the tableau. Okay, so the tableau, so we have found, so the tableau has here something called the bases. The bases are related to the variables that are different from 0. So we have found S1 and S2 equals to 16 and 12, so we put it there. Then we have to write the coefficients here in the goal function. So here are the coefficients of the goal function. And we have to write the constraints. So the constraints, it is 2, 4, 1, 0. So 2, 4, 1, 0. And then 3, 2, 0, 1, 3, 2, 0, 1. And actually, this is an equation system. So 2, 4, 1, 0 times 0, 0 for x1 and x2, and 16, 12 for s1 and s2. So if you substitute 0, 0, 16, and 12, then that is 16. And if you substitute here 0, 0, 16, and 12, this is equal to 12. So this is just writing the equation system in some organized way. Okay. And then we have to write there the coefficients associated to the basis. The coefficients associated to the basis, they are 0, 0. Very good. And then we will write something else. That is, you will multiply these coefficients times this vector. Okay. So 0, 0 times 2, 3, it is 0. So this is an inner product. Okay. So it is 0 times 2 plus 0 times 3, and 0 times 4 plus 0 times 2. So we have this inner product, and then this 0 for all of them, and the same here. Okay. So 0, 0 times this thing gives us this value. So actually, this value is the value of the goal function for your current solution. So your current solution is x1 equals 0, x2 equals 0, s1 equals 16, s2 equals 12. And then if you substitute that here, what you get is 0. So this 0 is the value of your goal function for the current flow through. And we will call this line, we will call it set J. Okay, so then set J is the profit to give up if added to the if we add it to the basic to the basis. Okay, so if we add this variable, if I add x1 to the basis, what do I have to give up? I have to give up 0 because actually x1 is not in the basis now. Okay, then we will compute Cj minus Zj. Okay, so Cj is this thing here, and minus Zj, that is this line there. So it would be 7, 6, 0, 0, minus 0, 0, 0. So it is that thing. Very good. And this is our first, this matrix is called tableau. We have the first tableau. And we have already this solution. Okay, very good. Then we finish the algorithm if this line here is smaller or equal 0. So as long as you have positive values, you don't stop. So this is not a smaller or equal 0, so you continue. Okay, so you continue, and then you have to decide which variable is the most interesting to get into the basis. So actually this was how much you have to give up if I remove one of the variables. This is the opposite. How much I'm gaining if I put x1 into the basis. So I'm gaining 7. And so x1 is the candidate, the best candidate to get into the basis. And then I have to decide, okay, the basis can only have two variables. So which one I should get out of the basis? And for doing that, what we will do is to show that. So what we have to do is to divide B by this vector. Okay, so it is 16 divided by 2, 12 divided by 3. So this is 8 and 4, and you have to take the minimum of those. Okay, so the minimum of that one is this one. So x1 will get into the basis, s2 will get out of the basis. Okay. Okay. So then that element is called the pivot. Okay. So now it is like as when you were solving equation system. So that element will be used to diagonalize the rest of the matrix. So we will make this 1. And to make this one, you have to divide it by 3, then this row by 3. And then when you have it 1, you will subtract from the other rows. Okay, so let's do that. So yeah, S1. So we have constructed our new basis, that is S1, X1. So now you put here, these were the coefficients, so you put the 7 there. Then we are dividing this line by 3. So that coefficient is 1. So you divide the whole line by 3. So you see 3 divided by 3 is 1, 2 divided by 3 2/3, and so on. And now you use this line, this row, to make this row diagonal. So to make a 0 here in this position. So if I want to do that, what I have to do is this row minus twice this row. Okay, so we do that. That would be 0 for that one. So we are multiplying by -2, that line, and then You see, it is, we had here 2/3. So 2/3 times minus 2 plus 4, it is 8/3. So, okay. So this is linear algebra. So with this line, you make this element 0, so you have to subtract the first row minus twice this one, and this is the result. And the same for the B. So the B, you also have to do that. Okay, then we continue. So now we repeat the same process as before. So you have to multiply these coefficients times each one of these column vectors. So that is the balance here. Okay, so you multiply, and this is what you get. And if you multiply 0, 7 by 8, 4, then this is the 28. 28 is the value of the objective function at that point. And the solution now, the solution is x1 is equal 4, x2 is not in the basis, so x2 is 0, s1 is equal 8, and s2 is equal 0. Okay? And now we compute this set j minus cj minus set j. So now one is negative, the other one is not. So we don't finish yet because not all of them are negative. Okay, so then, which is the candidate to get into the basis? So it is x2 because it is the one that you get if you add it to the basis. Here you gain 0, here you gain 0, here you are not gaining, but you are losing. Okay, so then we have to find which ones, so this is the one that will get in. So we have to decide which one will get out. So the one that will get out, this ratio is 3, this ratio is 6. So the minimum is 3. So S1 will get out of the basis. Very good. And then we have our pivot element. So this pivot element, and we have to do the same. So we have to make this 1, and then with this one, make this 0. So we will repeat that. Okay, so now S1 gets out of the basis, and X2 gets in the basis. And the coefficients, so you have to put here the coefficients, 6, 7. This one you have to make 1. So you divide the whole row by 8 over 3, or it is the same as multiplying by 3 over 8. So you make it 1, and this is the whole multiplication of the row. And then you have to make this element 0. So what we do is you subtract, so the new row will be the old one minus 2/3 of the new first row. So I divide that, or that is the solution. And now we have this part of the matrix. It is identity, or not identity, but 0, 1. It is only made of zeros and ones, and only one in each one of the rows. Okay, now we repeat the same. So we can multiply the coefficients times each one of the vectors. This is for the basic elements, how much you have to give up if you get x2 or x1 out of the basis. So if you get x1 out of the basis, for each unit of x1, you're giving up 7 units in your goal function, and the same for x2. And these two, they don't have any interpretation because they are not in the basis of your solution. So you are not giving up anything. Okay, then, yeah, 6 times 8, sorry, 6 times 3, plus 7 times 2 is 32. This is the value of your objective function. And the current solution is x1 equal 2, x2 equal 3, s1 equals 0, s2 equals 0. Okay, because they are not in the basis. And then you repeat the same thing again. Cj minus Zj. Now all of them are negative. And now you stop. So the final solution is this one. Okay. And we can draw it because this is a very simple problem with only 2 variables. So we can make the drawing. So the drawing, these are our constraints. So we draw 2x1 plus 4x2 equals 16. This is one of these equations. The other one is this one. And then the feasible region is this one, that is a smaller or equal, a smaller or equal. So this is the intersection. We started here and we started to move in this direction. So the first time x1 got into the solution. So we started at 0, 0. Then x1 got into the solution. You may remember the first solution for x1 was 4. So actually we went to this coordinate. And then after the second iteration, we have gone to this one. And you can imagine that this goal function somehow has an hyperplane that grows in this direction. That grows in this direction. And then we have reached that corner as the solution of the problem. I think that's all. Now he's explaining that. And this is our optimal solution with Z equal, so the goal function equal to 32. And yeah, so this is all. Any question? How to do this? You know how to solve linear equation systems with diagonalizing the matrix, right? Okay, so it is just doing that. So let's go back to our slides. Then let's repeat it now with our linear problem with the lambs. So let's see if we can solve it this way. So this was our original formulation. So we wanted to maximize the profit subject to some constraints, and we solved it graphically, and we saw that okay, we have to move. So this was this problem here. So and we reasoned we have to go to this corner. Okay, very good. Let's see if we find it. Here. Okay, so first step is to put the slack variables to turn the inequality constraints into equality constraints. So we add the slack variables and we start with the tableau. So as we said, the first basis will be the constraints. So we set x1, x2, x3 set to 0, and then the basis is just the constraints. So the constraints, they will be 100, 20,000, and 1,200. 100, 20,000, and 1,200. And I have called this the right-hand side. Okay, so because they are in the right-hand side of this equality constraint. Okay, and then this is our, so the coefficients, I have not written the coefficients. We have here the CV. The CV is the coefficients associated to the basis. And then we have here the equation system. The equation system, again, this is coming from the constraints. So the first constraint is x1 plus x2 plus s1 equal 100. So we have 1, 1, 1 equal 100. The second constraint is 120, 200, s2 is equal to 20,000. So we have 120 to 100, 0, 1 equal to 20,000. And this is the third constraint. So the third constraint was 10, 20, 0, 0, 1. So we have 10, 20, 0, 0, 1 equal 1200. Okay, so now set J, so set J is the product of these coefficients times all these column vectors. So all coefficients have 0, so all this is 0. And then Cj, that are the coefficients of each one of these terms in the goal function, minus Cj, minus Zj. So this is what we get. And then the maximum is 400 here. So this is the variable to get in. So the first variable to get into the solution will be x2. And then we have to find which one is going out. And then you remember it's the right-hand side divided by this column. So the right-hand side divided by 1 is 100, divided by this is 100, and then this one is 60. So this is the minimum, and this will be the variable going out. Very good. So then we have to manipulate the matrix. So x2 gets into the basis. So x2 gets into the basis, and we have to make this element, we have to make it 1. So we divide the whole row by 20. So we divide the whole row by 20, and we have this 1. And this is the new row. And this is CB, that is the coefficient associated to x2 in the goal function. And then with this row, we have to make the other rows in the same column, we have to make it 0. So we find the appropriate operations. So the operations would be this row minus 200, the new one here, and this row minus this one. And you make them 0. And these are the results. And here you have the right-hand side. It's not so. Okay, so now we repeat the process. So we compute set J. Set J is these coefficients times each one of these column vectors. So we have 200, 400, 0, 0, 20, 24,000. Right. So then set Cj, so the coefficients on top minus Zj. So we have this one, this is the maximum. So this is the new variable to get into the basis. And which one leaves? So we compute the right-hand side divided by this column. So it is 80, 80, 920. So we have to decide between S1 and S2. We don't care. We take the first one. And so X1 will get into the basis and S1 will leave. So again, we have to make this element 1. So we have to divide by. So, and with this one, we have to make this 2 elements 0. This is what we have done here. So this is 1, and then the 2 elements are 0. We already have these zeros. And then this is the updated table. And now we compute Zj, we compute Cj minus Zj, and now all of them are negative. So the final solution is x1 equal 80, x2 equal 20, and the goal function is 32,000. Let's see if that is consistent with our drawing. So in our drawing, x1 was 80 and x2 was 20. Okay? And the goal function is 32,000. So it is a little bit more than the last line we draw. Okay. So yeah, this is the final. Okay, any question up to here? No? I think it is a good point to make a break. Let's continue. So now we will go back to and we will discuss now something that appears in linear programming that is called duality. So duality is we have posed our linear problems this way. So some linear mode functions to maximize subject to some inequality constraints and these non-negative constraints. We have posted in this standard code the slack variables, but this is equivalent to those ones. Okay, so the dual form, this is called the primal problem. So the primal problem is kind of the first version. It is a problem in which you are maximizing something. The dual problem, it is minimizing something. And we introduce new variables that are the primal is formulated in X, the dual is formulated in Y. And we play a little bit with the locations of these vectors. So you see, this is C transpose X. So C is in the goal function. Now C will be in the constraints. The constraints before they were AX smaller than B. Now it will be A transpose. So A goes to A transpose. BC that we said that is coming from the goal function. And then the B before goes to the goal function in this B transpose Y. And it turns out that the solution of these two problems, they are very much connected to each other. So they look like kind of similar problems, not exactly the same problem, but the solution of the two are connected. Actually, the goal function is the same one. So if the goal function before it was 32,000, the goal function here will also be 32,000. So the maximum here that was 32,000 will be the minimum of this function that is also 32,000. And this is called the dual problem. So we have the primal problem and the dual. And there are some reasons to do this. And actually, this is what I just said. So if the primal problem has an optimal solution X star and the dual solution has an optimal solution Y star, then the goal function of both problems take the same value, the 30,000. And there is also this theory that says that for any feasible X in the primal problem and any feasible Y in the dual problem, the goal function of the primal problem is always the smaller or equal the dual problem. So it is as if, say, this is capital problem, okay? But I will make this drawing. The drawing is not accurate, but this more or less it conveys the right idea. So let's say that somehow I'm representing here X and Y. And here I'm representing the goal function of the primal problem. This is the goal function and the goal function of the dual problem. Now it is not accurate because those are hyperplanes. I cannot draw hyperplanes nicely here. But let's say that they were not hyperplanes. So let's say that one is like this, the other one is like this. Okay, so this is the optimum of both problems. This is where X star, Y star is. And for one of them, so for any value that is feasible, so for any value here, this value is always smaller than all these ones. So this is what this weak duality theorem is saying. Okay, very good. Then let's see why dual problems are useful. So let's say that we are given this problem to maximize. So we have many variables to touch on. So this x1 to x5, and we are just given two constraints. So we already know how to solve this with the simplex method, but it takes more steps because we will make. So if you count the number of steps, simplex steps that you have to do, because you have many variables on the objective function, it will take longer. But now let's formulate the dual problem. So if you formulate the dual problem, now there is one variable per constraint, but we have very few constraints. So we have very few constraints here. So we have very few constraints. So now we only have two coefficients in the goal function. And we have now many constraints. We have one constraint per variable. So actually the constraints, see, it is. So let's look at how it was before. So it was A transpose. So A transpose was AX plus Y plus 5. Let's write A for this one. So we have more than effect. This is 1, 1, 1, 1, 6, 1, 1, 1, 1. The other one is 2, 3, 1, 4, 2. 2, 3, 1, 4. This is smaller or equal 100, 180. 100, 180. So now our dual will be this one. So now it will be A transpose. So this one is A. This one is A. So now we have to write A transpose. A transpose. So A transpose 1. And then 2, 3, 1 times Y. Larger or equal the coefficients of the goal function. The coefficients of the goal function is 3, 5, 2, 7, 4. 3, 5, 2, 7, 4. 3, 5, 2, 7. So these are our constraints. Is what is written here. So here it is written in not in matrix form. So now it is much easier to solve. Even this is a two-dimensional problem. You can draw it in and if you count how many steps in the simplex, it will be fewer because once you make two ones, all the rest of the elements in the column will be zero. You have to make so many calculations, but it is a matter only of convenience. Okay, and we will see more properties of the dual. It is also giving you some information about the first problem, but at the moment it is just a matter of convenience. Okay, any question? No. Very good. So then, let's move on a bit and let's introduce something. This applies to simplex problems or to linear problems, but also applies in general to any modeling. So the sensitivity is we are finding an optimal solution. So now you may wonder, so we are maximizing this problem, this function with these constraints. And now you wonder, okay, what if my constraints change a little bit? will the optimum will very much affect it? And the other question is, what if my C's, my coefficients also change a little bit? Will I change, or how do I change the optimal solution? That is this sensitivity, and this is this sensitivity analysis. So in general, it can be formulated in this way. So you have some data, but you know that this data has errors. And with this data, you compute some model, and then you know that because you have errors here, the coefficients of your model will change. So that is uncertainty analysis in general, not in this optimization setup. And the sensitivity analysis is somehow how each one of these constraints translate into changes into your, how much each one of these variables is contributing to this uncertainty analysis. So all the coefficients that we have here, so this 100, this 180, so they're subject to errors. So if they are subject to errors, then how do these errors translate into my solution? This is in general the concept of sensitivity and uncertainty analysis. Okay, so let's see how to do that with linear programs. So let's consider this problem, and let's consider the dual. Okay, so X star is the solution of the primal problem, and Y star will be the solution of the dual. And each one of the components in the dual tells you how does the original goal function depend or vary with respect to B. Okay, so the shadow is how much each one this function changes as a function of these B's. Okay. In the primal, these B's is defined from the primal. So how much the goal function depends on the constraints, on every single constraint. So if the shadow price, this is called shadow price, not only in economic setups, but in general, Y star component, they are called the shadow price. So if Y star is 0, then that means that increasing or decreasing BI has no change, because it is not bound. This is like here. I think one example before. This was the constraint of the budget. If I give you more or less budget, it does not affect the solution, because you are not constrained by budget. You're constrained here, you're constrained by land and by labor, but you are not constrained by budget. You see, this optimal solution is not on the border of the budget. It's in the border of labor, and it is in the border of land. And even if you had a budget constraint, that budget was over what you needed. So for that one, changing the budget doesn't change the optimal solution. So for that one, the shadow price of budget will be 0. Okay. Shadow price of budget will be 0. And if it is larger than 0, then that tells you that increasing BI will give you a positive gain, and the opposite. If it's smaller than 0, that means that decreasing BI will give you a positive gain. So that resource is the one that is limited. Okay, yeah.
Oh, right. Right, geometrically talking, it's kind of like a projection.
It is somehow related to the fact that geometrically speaking, that the hyperplane defined by that inequality is not touching your solution. It's away from your solution. Yes, yes. Okay, good. Then we can compute this sensitivity into the objective coefficients. So we have talked about sensitivity to the right-hand side. Okay, so now sensitivity to the objective. So if the objective coefficients change a little bit, how does the solution change? So yeah, Cj is the coefficient multiplying xj. And then we can analyze the range for which the current optimal solution stays open. Okay, the optimal will be different. So let's say that in this problem here, so let's say that the profit of the corn is not 400, but 401. Probably the solution is still the same one. So the solution is the same one. The maximum value is not the same one. So the maximum has changed, but the solution is. So can it go from 401, 402 up to which value, such that the solution is still the same one, even if the maximum is not? So that is what we are asking. And what we will do is this calculation. So it is Zj minus Cj. So somehow this will give us something called the reduced cost. And if xj is non-basic, then this reduced cost has to be smaller than zero. That was actually our finish stopping criterion. And here I was showing in the Tableau how to calculate this thing that we did very easily. But if you want to be general, then it is this thing. So it is CB transpose. So CB was the vector associated to the vector of coefficients associated to the basis. So CB transpose times AB minus 1. So AB minus 1 is the part of the matrix associated to the basis. So the part of the basis is associated with the basis. The basis here, at the end, it is an identity, but in general, so at the end it is identity, but in general, in the basis, you don't need to have the identity. Okay, so here it's not updated Tableau. In the initial Tableau here, you see S1, S2, S3, yeah, it seems to be identity, but there might be general cases in which it is not identity. Okay, then it is CB transpose, AB minus 1, and then the column of the variable you are considering. Okay, so this is the general way of computing just one step. If you are following the steps of the Tableau, the simplex, then it is easier to do it this way. Okay, so let's try to do it for this example. So we have given you the theory of how to compute the sensitivity to the B's, sensitivity to the C's. Let's apply to our problem that we have just solved. So let's start with the sensitivity to B. So we said that our constraints were 100 hectares and 20,000 euros for the budget and 1,200 hours, labor hours. So let's say that they change it. So we can compute the shadow price. So the shadow price is so this is the shadow price. So this was our final Tableau. So in the final Tableau, you compute Cj minus Zj, you have minus 100 minus 10. But actually, these are related these dual solution. So the shadow price is here. Okay, so then the shadow price of the S1 is minus 100. Okay, so the shadow price, this was the land constraint. So the land constraint, the shadow price is 100. The shadow price of the budget is 0, and the shadow price of labor is plus 10. So it's the negative things and the negative things. Okay, so how to interpret that? So it is for each extra area that you have of land increases the profit by a factor 100. And for every new euro that you add to the budget, that doesn't change the maximum. And every extra labor hour will increase the extra the profit by 10 euros. So if you have to go for just one more unit, you would go for one more unit of land, not one more unit of labor hour, because it would increase the maximum value by more if you increase your land than if you increase your labor. You have to also see what is the cost of this one extra area. Okay, then yeah, so just a reminder of this. So we have these constraints. These be in the original matrix was this one. This is the initial tableau. So at the end, our basis was x1, x2, and x2. I go to the original tableau and take x1, x2, and x2. So you see that this matrix B is not in general, it is not zero. And what we are seeing is, okay, my solution, and this is the right-hand side. So in the basis, so these are my right-hand side in the basis. So my solution is B minus 1 BB, B minus 1. And what we have been doing in the sequence is inverting B minus 1. It's inverting B. Very good. So, yeah, so this is our solution. Now, what happens if I perturb the bits? So if I perturb the right-hand side. So I will get the original solution plus some perturbation. And we want to see for which range of perturbations this is larger or equal. Okay, so now multiply B minus 1B. And this is what we get. So this is B. Okay, now we have, so we substitute this by B1, B2, B3, so in general. And now we can study for which values of B1, still the solution doesn't change. So the solution is still larger than 0. So we this is in general. So in general, you fix two of them. So B2 and B3, take the values from the original. And then we study these inequalities for B1. Okay, so this has to be larger than 0. So this is B1 larger than 0. This thing minus 100 B1 plus 2 has to be larger than 0, which means that B2 has to be larger than 100 B1. And these three, this thing here has to be larger than 0, which means that B3 has to be larger than this thing. Okay, now we fix all of them except one. So we fix on this. And then we see which is the range for B1. So B1 has to be larger than 0. Then from the second one, B1 has to be smaller than B2 divided by 100. B2 divided by 100 is 200. And then from this one, B1 has to be smaller than B3 divided by minus 10. B1 has to be larger than this. So if we put all this together, B1 has to be larger than minus 120 and smaller than 200. So because B1 has to be larger than 0, then this is the final range. So the solution that we currently have will be the best solution as long as B1 stays between 0 and 200. So the line stays between 0 and 200. Then the same for B2. So you fix everyone except B2. So B1 was 100, B3 was 1200. Okay, so from this equation, we know that B2 has to be larger than 100 B1, but B1 is 100. Okay, so as long as B2 is larger than 10,000, then the optimal solution will be the current one. And actually, so this was the budget. So our budget was 20,000, and the optimal solution is the solution we got will be optimal as long as the budget stays larger than 10,000. So if it goes to 10,000, then if it goes to 10,000, then this line goes to this point. So it goes down, 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 down to this point. And if you keep lowering it, then now you are constrained also by budget. You are not only constrained by land and labor, but at some point you are also constrained by budget because this line has got into the feasible region. Okay, then for the labor is the same. So you fix B1 and B2 and you study B3, but B3 is only involved in this constraint. So B3 has to be larger than minus 10 B1. So minus 10 B1 is minus 1,000, but the labor hours so have to be larger than zero. So the only constraint is B3 larger than zero. So there is no upper bound. So this will be the optimal solution as long as the number of labor hours is larger than zero. So now we have ranges of B's for which the solution that we have found is the optimal. So this is our summary for the B's. So these are the ranges. So these ranges do not guarantee that the optimal values X star or the objective remain the same, but what they ensure is that the set of active constraints remain the same. So which are the active constraints here? The active constraints. So you have three constraints. This one, orange, blue, and green. And the active ones are the blue and green. The orange is not active because it is far away from the visible region. So as long as those ranges for these are true, then these are the active constraints. That is what they guarantee. The shadow classes remain valid, and the structure of the final syntax tableau. So what are the basics? The basic variables, they don't change either. And the solution varies linearly and predictably with PI. So you simply have to change PI this way, get more or less goal function. Okay. Very good. Any question? Yeah. Okay, so this is just the interpretation of yes. Okay, so now let's do it for the C's. So let's do it for the C's. And now we analyze the last row, that was this one, CJ minus 78. And then we said, okay, the reduced cost, this X1, X2, and S2, the reduced costs are zero. So those are the ones that are in the basis. And the shadow price of S1 is minus 100. The shadow price of the S3 is minus 10. Very good. And so what is that? What is that? that means that we are optimal for the current coefficients. These were our current coefficients. And if you increase C1 or C2 slightly, so slightly is just a little bit, the current basis remains optimal. If you decrease them slightly, one of them may become non-basic. So if you increase, the solution is the same, but if you decrease, one of them may become non-basic, so may get out of basis. And we can solve for which are the ranges for C1, C2 by solving this inequality, the same way as we did for the B's. So for the B's, we have to solve this inequality. Okay, so let's do it for the C's. So for we take all the non-basic variables. So the ones here will be S1 and S3. And we have to study for which ranges they would still be smaller than zero. These reduced costs are still smaller than zero, because if they are zero or larger than zero, they will get into the basis. Okay, so for which values of C's, they still stay there. Okay, so then this was the column for S1, and this is the column for S2. So we have to multiply, we have to compute Z. Okay, so compute Z, we have this C, this C times this one. This is our, so in general, okay, so this was C1, C2, C2. So now we forget that we have 300 and 400, and we put in general C1 and C2. So what we have is 2C1 minus C2, and that will be our result. Okay? So 2C1 minus C2. And then what is this? What is this term here? So this term here is the coefficient of this one, that is 0, minus this thing. So it is 0 minus 2C1 minus C2. And that gives you an inequality. And the same for S3. So you multiply C1 minus 0.1 plus C2 plus 0.1, and that gives you this thing. And then Z, so C minus Z is here, so that gives you another constraint. Okay, so if you summarize both constraints, these are the two constraints. So C2 has to be between C1, so C2 has to be larger than C1, but smaller than 2C1. So as long as C2 is between C1, so C1 was 300. So as long as it's between C1 twice as C1, the solution will be the same one. The solution doesn't change. And we have computed here C2 as a function of C1, but you could compute C1 as a function of C2. And this will be your result. So as long as C1 is between C2 and half of C2, then the solution will be optimal. So as long as the profit of the wheat is somewhere between 200 and 400, or the profit of the corn is somewhere between 300 and 600, the solution you have found is the optimal one. So what we have learned is how to compute the optimum of a linear program, and then how to evaluate for this optimum as a function of C1's, so my coefficients and my constraints. If I change the coefficients, so if I change the constraints, is my optimal solution still the optimal one? That is what we have. Then we have seen how to compute those ranges for the coefficients, how to compute those ranges for the constraints, and then how a change in the constraints would affect the final ball function. Okay, any questions?